Look at the scale of this system. This is an extreme ultraviolet lithography machine by ASML. It is currently the only piece of hardware capable of printing the dense, complex circuit patterns required for the world's most advanced microchips. But to print those microscopic transistors, the process begins with a violent event. Deep inside a vacuum chamber, the machine generates a continuous plasma explosion. But this creates a direct engineering paradox. The exact explosive mechanism required to make the machine function inherently tears it apart from the inside out. To generate extreme ultraviolet light, the system fires microscopic molten tin droplets into a focal region at an astonishing rate of 50,000 times every single second. A two-stage laser targets the droplet. First, a pre-pulse hits perfectly dead center, flattening the sphere into a pancake shape to maximize surface area. Instantly, a high-intensity main pulse strikes the target. The tin vaporizes, creating a highly ionized plasma 40 times hotter than our sun. Inside this ultra-hot environment, the tin ions undergo extreme electronic transitions. This violent 50,000 Hz heartbeat emits photons at exactly 13.5 nanometers, the specific wavelength required to print patterns at the atomic scale. All of those scattered photons have to be captured and focused by the machine's most sensitive optical element, the collector mirror. To reflect such short wavelengths, it is built from 100 alternating layers of silicon and molybdenum. The manufacturing precision here is difficult to conceptualize. If you scaled this mirror's surface to the size of Germany, the highest topographical deviation would be a mere 0.1 millimeters. But the explosive vaporization of the tin droplet creates a devastating byproduct. Fast-moving ions, neutral atoms, and scattered molten tin radiate outward from the ignition site, moving on a direct collision course with the perfectly polished optic. A microscopic deposition of tin ruins the mirror's reflectivity. Without mitigation, the physical bombardment of this debris would destroy a collector mirror in exactly 60 seconds of operation. Solving this bottleneck ignited a fierce corporate engineering race. The initial mitigation strategy relied on powerful electromagnetic architecture. Engineers used superconducting magnets to sweep away the highly charged tin ions, redirecting them into traps. While magnetic fields handle charged particles well, they are ineffective against fast-moving neutral tin ions and diffusing vapor. The magnets alone couldn't stop the debris wall. The industry eventually adopted a brute force chemical solution. Look at this diagram. A massive cross-flow of hydrogen buffer gas is pumped in to intercept and slow down the high-speed particles. Furthermore, hydrogen radicals chemically react with the deposited solid tin, transforming it into a volatile gas called stannane. Stannane is extremely hazardous. It is highly toxic and violently flammable, and requires specialized high-capacity vacuum pumps to safely extract it from the facility before it can damage the optics. This application of industrial chemistry allowed collector mirrors to survive for hundreds of billions of pulses. If you appreciate the brutal realities of these hidden engineering systems, take a second to subscribe to the channel. But solving the debris wall birthed a secondary failure mode. The hydrogen gas introduced to save the mirror interacts disastrously with its protective outer layer, a metal called ruthenium. While the hydrogen gas effectively etches away the bulk of the tin, it leaves behind a microscopic trace. A single, unremovable atomic layer of residual tin remains chemically bonded to the mirror's surface. This single atomic layer acts as a one-way catalytic valve. It dramatically lowers the energy barrier for the gas, allowing small hydrogen atoms to easily slip downward through the tin and penetrate into the ruthenium lattice below. Because the top surface remains saturated, the trapped hydrogen is blocked from escaping. The atoms pool, multiply, and expand beneath the surface. This creates intense localized pressure. Microscopic pockets of gas physically deform the metal, creating atomic blisters that rupture the perfectly polished mirror from the inside out. The blistering of the ruthenium cap demonstrates a recurring theme in extreme engineering. You rarely achieve an absolute fix. You simply trade one physical limitation for a more complex one. Yet, despite this atomistic war, the system maintains enough stability to function. Look at the brilliantly patterned silicon wafer in this image. It is the physical result of successfully managing that internal chaos. The ability to maintain this equilibrium, preventing a few layers of tin and hydrogen from destroying the source, is the prerequisite for high-volume manufacturing at the 5 nanometer node. Without this specific balance, the hardware required for modern artificial intelligence simply couldn't be produced. Because this technology is so central to advanced logic, these machines have become the most tightly controlled assets in global trade. Click the video on your screen to see how the race to control this specific supply chain is unfolding.